Welcome students. This is the third session in Control Systems Engineering. In the previous session, we saw signal flow graphs, block diagram reduction techniques, and Mason's gain formula. Moving on to the next, we have transient responses. Now, what is a transient response? I had given a slight idea in the introduction session. While describing the input-output condition or the input-output relation of any system, I described there are two types of outputs. One is a steady state output and other is a transient output. So one of the output type is steady state output. And the another output type is transient output. Because systems are not perfect and they cannot mirror the practical scenarios completely, you get two types of outputs. The system takes some time to reach its ideal value, which is a steady state value. And while reaching to its steady state value, the output value of any system varies and struggles to get to the steady state value, which is known as a transient phase of the output. These transients are important because we have mechanical systems. We have to practically model the systems, and hence to understand the limitations of the system, transient responses are important to study. We'll go forward and check what will you learn in this particular session. Before going into outputs, we must study what kind of inputs that we are interested in giving to the system. There are many standard inputs known as delta function, step signal, ramp signal to be given to a system. Now these inputs are studied in time domain also, and also their Laplace transforms are important when we are studying control systems engineering. Later on, we move towards first order systems. First order systems are simpler systems, and we are going to study first order transients. Later on, we will be coming towards second order systems, which are little complicated systems than the first order systems. But second order transients are equally important because many systems can be generalized according to a second order system. After that, we will be studying typical second order parameters which govern or which characterize a transient response of a second order system. We will look at important formulae and we will conclude the chapter later. Let us go forward and check what are the typical input signals. As I already described, there are delta function, step signal, ramp signal, parabolic signal, and also their Laplace transforms. So, typical signals are shown. Their name is on the left, and you can study the figure. You can check the figure of that particular signal on the right hand side. As you see, impulse signal, which is also known as a delta function, is represented as delta t. So delta t is nothing but a signal existing at t equal to 0 with infinite magnitude, not literally, but for very small time, if you get a very large magnitude, so that area under that curve is equal to 1, we call that function a delta function. The Laplace transform of a delta function is equal to 1. So this is a very unique property of a delta function. The the Laplace transform of delta function is equal to 1. Then the second basic signal is unit step signal, which is represented as u of t is equal to 1 for t greater than equal to 0, whose graph can be seen as equal to this. For 0 to positive time, we have amplitude equal to 1, but before 0, you have amplitude 0. So, the Laplace transform of u of t is equal to 1 is equal to 1 upon s. So, this is a important Laplace transform because often we subject a system to unit step signal and study their responses. Further, you have ramp input, which is nothing but a slope with value 1. So, r of t is equal to t. So, if you have t on x-axis and r of t on y-axis, so you have this angle is equal to 45 degree as r of t and t are equal, and hence you get slope is equal to 1. So, this is the standard signal which is subjected to some of the system. The Laplace transform of a ramp input is equal to 1 upon s square. As you know, for a time domain signal represented as t raised to n, its Laplace transform can be given as n factorial upon s raised to n plus 1. So in this case, t raised to n small n is equal to 1, we can transform t as 1 factorial, which is 1, and s raised to 2. So there you go. You get 1 upon s square as a Laplace transform of r of t is equal to t. Then you have parabolic input, which is represented as s of t is equal to t square by 2. We can represent any parabolic input as power of 2 of time t, but the Laplace transform of t square by 2 is 1 upon s cube, and that is why t square by 2 is a standard signal. So all these inputs have Laplace transforms in order 1 by s. So here is 1, then you get 1 by s, then you get 1 by s square. For parabolic input, the Laplace transform is 1 upon s cube. And for sinusoidal, as you can see here, the amplitude is 1 and frequency is omega. And then you have the Laplace transform as omega upon s square plus omega square. Omega upon s square plus omega square. For sinusoidal input, the numerator is equal to the frequency of the signal. And for a cosine signal, say cos omega t, the Laplace transform is s upon s square plus omega square. That is the only difference between a sinusoidal input's Laplace transform and a cosine input Laplace transform. This is how you can define the typical input signal. You can study the graph. Let us remove all those ink annotations so that you can see clearly. Anyway, so this is how you can check the typical input signals. Let us go forward and check the first order systems. As I already described, in first order systems, we will be looking at the time domain first order systems. Then we will see how the Laplace transform of first order system looks like. Moving on to first order transients, we will start with the first order system basics. So a first order system is nothing but the first order differential equation containing system. So say if you have a differential equation as dy by dt plus y is equal to x, then this system is known as first order system because the order of this system is 1. Now if you take a Laplace transform of this equation, you will get s into y plus y plus is equal to x. I have introduced capital Y for small y and capital X for small x, and then you have s into y. Then I will get, taking y as common, s plus 1 is equal to x, and therefore the first order transfer function will be Laplace transform of output upon input, that is y by x will be is equal to 1 upon s plus 1. So this is the Laplace transform of this example. Now this is how a general first order Laplace transform looks like, wherein you have the degree of s is 1 in characteristic equation. Characteristic equation is nothing but the denominator of a transfer function. So here, as you can see, power of s is 1, and hence this is known as a first order system. The coefficient of s when first term is 1 is known as time domain, time constant of the system. So herein the capital T is equal to 1 in this particular system, hence the time constant of this system is equal to T is equal to 1. Okay. We will move forward and see how exactly the response of first order system looks like. We'll be studying the response of any first order system, say first order system. To get the first order system, we will subject the first order system or any system with a unit step function u of t, which is equal to 1 or t greater than equal to 0. Now the Laplace transform of u of t is nothing but 1 by s, and we will study the response of this particular system, assuming that we know the transfer function of this first order system, which would nothing but of this kind, k upon 1 plus st. Okay. Now while subjecting this input to the transfer function of this particular system to generate the output, we will have to multiply these two signals. Let us go forward and see how we can do that. Now in this particular system, you can see there is a first order Laplace transform. So this is a first order system. Okay. Now you have step input u of t, whose Laplace transform is nothing but 1 upon s. Now we are going to multiply 1 upon s into k upon 1 plus st. If you do that, you get 1 by s into k upon 1 plus st, which gives k upon s into 1 plus st. Now if you simplify this or make partial fractions of this particular function, you get k into 1 upon s minus t upon 1 plus st. So that's what we have written here. Now converting this Laplace transform or frequency domain output into a time domain output, because we are interested in first order response also in frequency domain and in time domain both. Why are we interested in time domain response? Because then we'll be able to plot the graph of this particular time domain response. As we can already see, we have got the frequency domain output, which is k into in bracket 1 upon s minus capital T upon 1 plus ts. Now as we can see, if we convert this particular Laplace transform again into time domain, we will get k into time domain transformation of 1 by s, which is nothing but u of t. But as we know, time starts only after t equal to 0. So it is nothing but is equal to 1. So k into 1 minus t into 1 plus ts. 1 upon 1 plus ts is the Laplace transform of e raised to minus small t by capital T. So this is what is written after k. So this is a time domain response of a first order system. Also remember, for any system in mathematics, you will see while solving the system, you will have two solutions. One will be complementary function and other will be particular integral. The complementary function is nothing but a transient response of the system, and particular integral is steady state output. Again, in this particular time response, we are seeing two terms. One is equal to k and the other is having term e raised to minus t by tau or capital T. You can model k as a steady state output, which is a constant, and for e raised to minus t by tau, which is a decaying or elevating system, it is known as a transient output. So every output would have two parts. Let us go forward in the next slide and check the graph of this particular system, wherein you will be seeing the significance of this steady state k and the significance of the transient k into e raised to minus t by tau. In this particular slide, we are able to see the graph for the first order response curve. And as you can see, the expected value for this particular system is k. But this is attained after certain amount of time. Before that, you get a transient response where system is struggling to get to reach to k. Okay. So here we have value 0, and after some amount of time, the value reaches to the desired k value. As you can see, we had the response as k minus k into e raised to minus small t by capital T. Now, the complete response is modeled as the addition of transient response and the steady state response. Our input was step input. Sorry for the curve. Our u of t is the input, and our system was a first order system with responses like this, k from 0. Just imagine a water heater. Okay, so if I have to heat the water from say 0 degree to 40 degrees Celsius, okay, if I on the heater, if I give the step input to the heater, which when I switch on the heater coil, ultimately my water starts to heat, but my water doesn't instantly go to 40 right from the time t equal to 0. It has to take some time to reach to 40. But water heater is a first order system which will follow this type of a curve to reach 40 degrees Celsius. Okay. Now, as the difference between the desired 40 degrees Celsius value and the 0 degrees Celsius value is more, so we have transfer of heat maximum, which is delta T, which is nothing but 40 degrees Celsius minus the current temperature of water, Tc, which will be maximum at the starting of the heating when Tc is equal to 0. As the temperature of water increases slowly, let us say at this point, the rate of change also reduces because delta T has reduced, because Tc is say at 20 degrees Celsius and the rate of heat transfer depends upon delta T, which has reduced, and hence the rate itself starts reducing. As water reaches 39 degrees Celsius mark, the rate of heat transfer reduces so much that it takes a further little time to reach 40 degrees Celsius. So this is known as a first order system. Let us go forward and see what is a time constant for the first order system. As we saw, we can model a first order system as k upon 1 plus st by making a constant term to be 1. Whatever is the coefficient of the term s, we call it a time constant. But what is the physical significance of a time constant of a system? We saw that a graph of any first order system is like this. So slowly this value reaches k. So a time constant represents the time taken for the output to rise to 63.2% of the change in output from the initial level. So if this is 100% k, let us say this is 0.63 k. Whatever time it has been taken by the system to reach 63.2% of k is known as time constant. In first time constant, system reaches 63% of the desired output. Then in the second time constant, system reaches to the 87%, which is nothing but 0.87% of the final output. In third time constant, system reaches 96% of the final output. As you can see, for equal times, the rise in output is lessened, and this is how first order system works. So this is the physical significance of a time constant. Safely you can agree that in 4 time constants or in 5 time constants, system reaches to its desired final value. Remember, all this analysis is done for step input, that is, input is equal to u of t. Let us go forward and see the second order systems. We have second order systems, and we will be studying the time domain analysis of second order system. Not analysis, we'll just see the representation of second order system in time domain. Later on, we will also see what is a typical general Laplace transform of a second order system, and we will also see second order transients. Let us go forward and see the second order system basics. As you can see, as we studied in first order system, a first order system is nothing but a differential equation in first order. Similarly, a second order system is nothing but a differential equation containing a second order term. So let us say if we have a system dy by dt plus d2y by dt square plus y is equal to x. So this is the example of a second order system in time domain. Taking its Laplace transform, you would find it is of the general form like this. As you can see, this is the second order system. The terms that I have used as k, omega n, zeta are some of the important factors or important characteristic parameters of a second order system. We will be studying them in the later slides. Just remember, k is a DC gain of second order system. Omega n is the frequency of second order system. Zeta, which is shown by this particular sign, is nothing but a damping factor of the system. Also, 1 upon zeta omega n is known as time constant of the system. As you can see in this particular function, the degree, highest degree of s, I forgot to write s here. So the function is k omega n square divided by s square plus 2 zeta omega n s plus omega n square. As you can see, the highest degree, highest power of s in the characteristic equation is 2, and hence this is a second order system. We will look at the following terms and the relations or the significance of following terms in the next slides. To solve this particular second order system and to split this into partial fractions, we can take the value of zeta from 0 to 1. Now, zeta can also be more than 1, but for this particular condition, for zeta to be between 0 to 1, which is nothing but a damping between 0 to 1, we get the time domain response as follows. C of t is equal to k into 1 minus e raised to minus zeta omega n t divided by root of 1 minus zeta square sine of omega d t plus theta. Here is a new term, omega d. Omega d is defined as omega n into 1 minus theta square. This is the time domain response for a system k omega n square upon s square 2 zeta omega n s plus omega n square. Okay? And the important condition to know is that zeta is between 0 to 1, which is known as underdamped system. Okay? Also, theta is defined as tan inverse of root of 1 minus zeta square by zeta, or cos inverse of zeta. So by the knowledge of zeta and omega n, you can totally model the system into its time response. We will put different values of t to find c of t. Now let us see in the graph how exactly a second order response looks like. A second order response looks as follows. As we already described, for a second order system of model k into omega n square upon s square plus 2 zeta omega n s plus omega n square, which when subjected to the unit step input whose Laplace transform is 1 by s, solving this function gives us c of t is equal to 1 minus e raised to minus zeta omega n t upon 1 minus zeta square into sine of omega d t plus theta. So this is the response that we get if you solve this and second order system. Plotting this curve with respect to t would give you a graph something like this, wherein zeta is between 0 to 1. Okay, so this is the important condition for such an output to occur. As you can see, this is a step response. That means we have the input of step, and our response has a steady state value after certain amount of time. As you can see, the system does not directly go to the desired value of 1. It takes some time. It goes above 1, comes back below 1, and then the transients slowly die out to get us to the desired value. So this is how a second order response can be classified into a transient response and later on the steady state response. Okay. Now, by looking at this particular diagram, we can easily say that the transients are important in the second order response. As you can see, there is a maximum value which is attained by the output. This maximum value depends upon the parameters such as zeta, omega n, and ultimately the system which is made up of such instruments such as resistors, capacitors, or inductors and their values. These values determine what are the values for omega n and zeta, and ultimately these also determine the value of such overshoots or the oscillations. Now, human might desire more oscillations but lesser overshoot. Sometimes a user requires more overshoot but less pulses before they die out. So, for a system design of a second order system, it is very much required to model the system according to user needs, and to know that we must understand what are the typical parameters which are governed to describe the transient response of a system. Let us go forward and see what are typical second order parameters. We will see some of the definitions such as overshoot and rise time, delay time, and etc. And we will see some important formulae to calculate these overshoots, rise time, delay time, etc. As you can see, this is a different version or different graphical version of a second order transient response. As you can see, the steady state response has not been shown. So this is just a typical second order transient response. As you can see, we have subjected the second order system to a unit step and we have different parameters. Now you can see value is going above 1 and then coming back, and the transients die out after some time. The first parameter is TD, which is shown here. A TD is known as delay time. Okay. Delay time, as you can see, is nothing but the time required by the output to reach the 50% value of the desired output initially. So delay time is nothing but time taken by the output to reach its 50% value. Okay. Then the next parameter is TR, which is known as rise time, which is nothing but the time required by the system output to reach 100% value initially. Okay. So delay time is nothing but 50% value of the desired output, and rise time is nothing but actual desired output and time required to be there. Now we have a third parameter known as MP. MP is nothing but maximum overshoot. Maximum overshoot is nothing but the percentage of value which is more than 1 attained by the first peak of the time response. Let us say this is 1.27, then MP value is 27%. Okay. Now TP is known as peak time. Peak time is nothing but the time required by the system output to reach its first peak. So peak time will be when the system output attains the value MP. Then you can see there is a parameter known as TS. TS is nothing but steady state time, or known as settling time. Settling time for an output. This is more commonly used term. What is a settling time? Settling time is nothing but when all the transients die out and the system output finally reaches into the proximity of the desired output. The tolerance of proximity is given by 5% plus minus, or sometimes 3% plus minus. We will now in the next slides study the formulae to calculate all these terms: TD, TR, MP, then peak time and settling time. Let us go forward and see. As I have already described, the definitions are as follows. You can cross check again. The delay time is nothing but 50% of output response, or the time taken by the response to reach 50% of the reference value. Rise time is 100% value and time taken to reach there. Peak time is time taken by the response to reach the first peak of the overshoot, as I described. And settling time is the time taken by response to finally settle and be in 3% or 5% tolerance band of the reference. These particular formulae describe how to calculate the typical second order parameters, which are very important. So initially we will study how to calculate rise time. So formula for rise time is equal to TR is equal to pi minus theta upon omega d. To calculate rise time you should know zeta and omega n. As you can see, theta is nothing but cos inverse of zeta and omega d is equal to omega n into root of 1 minus zeta square. So by the knowledge of zeta and omega n, you can calculate rise time. So say if zeta is equal to 0.5 and say zeta is equal to which is the better value to calculate, then you have zeta is equal to 0.5 and let us take omega n to be is equal to, let us say, around say 16. Okay, what would be my rise time in such a case? TR would be pi minus cos inverse of 0.5, which is nothing but pi minus pi by 3, and upon omega d, which is nothing but 16 into 1 minus 0.25. Calculating this, you get 2 pi by 3 upon 16 into 0.84 around, and if you calculate that, you can get 2 into 3.14 upon 48 into 0.84, which gives you 6.28 upon, which is close to 40, and calculating this, we would get 0.15 seconds. So for zeta is equal to 0.5 and omega n equal to 16, we will get rise time is equal to 0.15 seconds, which is a close value. I have just calculated this impromptu at this particular time. Let us see how to calculate maximum overshoot. Maximum overshoot is given by e raised to minus pi zeta n divided by root of 1 minus zeta square. So the whole power is first calculated, and then you will take the power to e. This maximum overshoot is calculated in percentage. So if this comes out to be 0.43, that means the overshoot is 43% and value is at 1.4. Okay, this n is nothing but the value of the nth peak. If you want to calculate the overshoot for first peak, then you put n is equal to 1, and for the second peak you might put n is equal to 2. But as you can see, the first peak is above 1, but the second peak is a little less than the first peak. So maximum overshoot is at n is equal to 1, and hence you put n is equal to 1. So e raised to minus pi zeta upon root of 1 minus zeta square will give you maximum overshoot. How to calculate settling time? Settling time is nothing but 3 times of the time constant, or which is nothing but 3 into 1 upon zeta omega n for 5% tolerance. And if you want to calculate the 3% tolerance settling, you will multiply a time constant by 4. So first you will calculate the time constant of the system by the knowledge of zeta and omega n, and then it will multiply it by 4. How to calculate peak time? Peak time is nothing but time taken by the system to reach its first peak. To calculate TP, the formula is n into pi upon omega d. So again, for first peak, you will have to put n is equal to 1, and then formula will become pi upon omega d. So as you can see, for every formula, you just have to know value of zeta and omega n. Here also zeta and omega n. Again zeta and omega n. Here also for omega d you have to know zeta and omega n. So if you know the second order system or the parameters of second order system, which are given by k omega n square upon s square plus 2 zeta omega n s plus omega n square, you would ultimately know the values of omega n and zeta, and you will be able to calculate all these parameters, and will have to, or you can successfully negotiate to the system designer what kind of system response that you are getting and how are the changes or what are the changes that are to be done in the system. Let us go forward and see the session summary for the chapter Transient Response. Initially we saw what are the typical standard input signals which are subjected to different systems, and those are impulse function, step signal, ramp signal, parabolic signal, and sinusoidal signals. We also saw the Laplace transforms of these signals. Then we moved forward and then we saw that system transfer function can be analyzed by subjecting a system to the impulse function, right? Because if you have a system, let us say system to be as equal to A, and I have to find out its transfer function. If I don't know the transfer function of the system, what should I do? I should apply a system with the impulse signal whose Laplace transform is nothing but 1, and whatever output, if I am able to measure my output y of s or say y of t, then I know what is the transfer function of the system is nothing but the Laplace transform of output upon input. So A is equal to y of s upon 1. So A is nothing but y of s. So this is how I calculate the transfer function of the system, by applying it by an impulse function. We also saw the systems can be analyzed in time domain and frequency domain. I'm sorry for this particular typo. It should be frequency domain. So systems can be analyzed in time domain and also in frequency domain. There are different advantages of analyzing systems into time domain as well as in frequency domain. We also saw the second order systems are characterized by different parameters like rise time, peak time, maximum overshoot, and settling time. Here we will end the transient response session. In the next session, we will be looking at steady state errors and stability. For now, we will end this session here. Thank you.